This is a Cisco RF Gateway-1, an edge QAM modulator used in cable headends for broadcast, video on demand, and DOCSIS. Today, we will be attempting to get this working with my server, and hopefully by the end of the video, we will be broadcasting our own cable programming from my home. This unit comes with an interesting bit of hardware that I have not been able to find any information about. This card slots into where a QAM modulator would go, and simply adapts some of the backplane to a DB25 connector. It's called the RF QAM bypass. However, I don't see what it could be bypassing, since this unit should be able to run without all the modulators installed. Turning the unit around, we can see it has the typical redundant power supplies, 8 total networking jacks, the 2 cards I was talking about. If you worked at a head end or cable plant and know what these were used for, please leave a comment. I'm very perplexed by these. And 4 QAM modulators. Both rows of networking serve a different purpose. The bottom row are RJ45s that support 10100 Ethernet, and are intended for network management through the web UI, while the top row are gigabit SFP ports that are used for network video stream ingress. Each of these QAM modulators support a total of 8 channels, meaning a fully populated chassis would be able to support 48 channels. Since I have these weird cards though, my unit is currently capped at 32 channels. That will be more than enough for what I'm planning to do with these, so I'm not losing any sleep over it. Now when working with QAM modulators, the term channel does not refer to what most people think. For what we are doing today, each channel is simply an allotted 6 MHz frequency in which data is transmitted. It does not refer to TV channels that you tune into with your set-top box. Those are called programs, and multiple programs are modulated into each channel. Depending on the bitrate used for the programming, you can have anywhere from 2 high-definition programs to 15 standard-definition programs per channel. There's a lot of technical know-how that goes into this broadcast engineering, and I am only scraping the surface of it with this. First, let's get this thing hooked up to the network. Since the theme so far is overkill, I've got these 2 large spools of RJ45 that I'll be using for a 5-foot run to my router. One thing that needs attention before starting is how these 2 cards have no casing to them. I believe this will lead to all the air flowing out over here rather than cooling the modulators. For the meantime, I'll restrict the airflow through these with just some microfiber cloth. But in the future, I might 3D print some plugs for these 2 ports. There we go. Now we just have to apply power and enjoy the cacophony of noise that this unit will generate. Oh, that's not too bad. Oh. Okay, that's more what I was expecting. Honestly, among all the networking equipment I've run, this is on the quieter side. I believe there's even a setting to ramp down the fans according to the CPU and modulator utilization. Quick aside about that, apparently the firmware on my unit is way out of date and does not include this feature. Worse though, the only way to get that latest firmware is through a support contract with Cisco. Now let's just check if the unit automatically acquired an IP for the management interface or if we'll need to set one ourselves. Perfect. Now we can go upstairs and start configuring the settings. Alright, now that I'm at my computer, we can check out this cool little rear port diagram. Quite cool looking in my opinion. We can also see a few errors, but it's only because we didn't have redundant power and we're missing 2 cable cards, so nothing to worry about. First, we'll go over to the system page and make sure that the encoding type is set to ITUB, which is the standard for North American broadcast television. Since it is, we can move on to networking. I'm not certain how the hierarchy of this works outside of it being redundancy, but I've gone ahead and assigned port pair 1 and port 1 their own IP addresses. I'm not certain if I need to set port 1 manually or not, might as well just in case. Now we'll head over to the QAMs tab and check out the configuration for the modulators. The main page is an overview of the crucial details you'll need to get at a glance, but we'll delve into the detailed settings for card 2, port 1. Here we need to make sure the port is enabled, which it is. On this page you can also configure the number of channels on this port and either their channel number or channel frequency. Changing one will change the other, so it doesn't matter which one. I landed on using channel number 14 for no particular reason at all. There are 2 modulation schemes you can select, QAM256 and QAM64. They both have their use cases, but we'll be using 256 since it has more bandwidth and we are doing a small run. There are higher schemes, such as QAM1024, but this system either predates them or just does not support them. Another very crucial thing to note is the channel output level. If I were to plumb this into a TV right now, it would more than likely fry its tuner due to how high it is. When this hardware is used in a head end, 50 decibel millivolts would be fine for distribution since there's going to be long runs, splitters, and other hardware on the line that will knock it down along the way. For our use though, it's at least 5 times too powerful. For cable, the ideal is about 0 decibel millivolts, with an allowed variance of plus or minus 10. Decibel millivolts is a logarithmic scale, meaning that negative 10 decibel millivolts equates to 0.316 millivolts. Next, we will head to the stream map. Here we will tell the system that our video feed is a unicast stream by keeping the destination IP at 0000. The alternative is that we have a multicast stream, which will require our Cisco system to reach out to the video server and tell it that we are interested in receiving its video stream. That's why the destination IP is a specifiable field. We can also specify if the stream is a single program transport stream or a multi-program transport stream. Since we are just broadcasting one MPEG transport stream, we will of course select SBTS. Last thing we'll do is make note of the UDP port that is set for QAM2 port 1, which is 51204. When we install this unit for actual use, we'll definitely be needing to configure more of the nitty-gritty settings, but for testing, this should hopefully be all that is required. We can now finally start streaming our video from the server to the QAM modulator. For this, we'll be using FFmpeg to transcode the MP4 file to MPEG-TS UDP unicast stream. This is the FFmpeg command we'll try based on my research and assumptions of QAM modulation. Let's break this down. Ignoring the FFmpeg boilerplate flags, we'll start with CV MPEG2 video, which tells FFmpeg to use the MPEG2 codec. Next is BV 3500K, which sets the target bitrate to 3.5 megabits per second. Max rate 3500K sets a ceiling on the bitrate, which is crucial if we want to keep a constant bitrate, and we do. Buff size 7K sets the buffer size and essentially tells FFmpeg how far ahead it can go before getting reeled back in. G15 specifies how often to send a new frame of video, which for us is every half a second. A smaller number means you get less artifacting when first tuning in or on loss of signal, but you get less compression that way. Next is the audio, with CA-MP2 specifying the use of MPEG-1 audio and BA specifying the bitrate of 192 kilobits per second. AR 48000 sets the sample rate of the audio to 48 kHz. Finally, we have the container information, which is MPEG-TS service ID 1 and FFmpeg-TS. The first is for the programming ID and is used by the set-top box to identify the program in the stream table. The next one simply tells FFmpeg that it needs to output using MPEG-TS. As for the URL, the standard UDP payload size for broadcast is 7 MPEG-TS packets, and with each packet being consistent 188 bytes means 1,316 bytes. TTL stands for time to live, and it limits how far a packet can travel through the network. I don't believe this is relevant for unicast though, let alone a small setup like ours. I'll be including it out of formality, and if our stream fails, this will be the first thing I shuck from the command. Now with that command running, we do already see signs of life on the dashboard of the Cisco modulator, which is very good news. Hopefully that means it's working, but there's only one way to find out. Back downstairs, taking a look at the front of the unit, we can see there's a good amount of activity on Gigabit Ethernet 1. Also, look at that cool Cisco art on the LCD. My audio quality drops off quite drastically for this next section for many reasons, but I didn't want to dub over the moment of truth. Off camera, I added the 10 decibel attenuators, and now all I have to do is just program the TV. Fingers crossed it works. All right, yep, perfect. Oh, it worked. Now we just have to see if it's all staticky, if it's black, or, okay, so far so good. Yes! Would you look at that? It works perfectly. This was by far the best outcome I could have imagined. Everything worked right out the gate without much fiddling at all. I was worried that I was going to be required to use a multicast stream or be stuck mucking about with the FFmpeg settings, but it all just worked. I can't think of the last time this has ever happened to me or anyone for that matter, but I'm so glad it did. At the end of the day, this has to be one of the most fun projects that I've done in a while despite its simplicity. I've always loved broadcast equipment, and the thought of having my own miniature television station has always been a dream of mine. And though I can't technically broadcast it to everywhere, I can at least have it in my own home. In the future, I would love to explore setting this up with an old Motorola DVR from the mid-2000s, possibly even using it with Ursat's TV, and so much more. If you're interested in that as well, I would recommend subscribing. Thanks so much for watching. Hopefully I'll have more content like this out regularly.